Hi, I'm Neil Feit of the Department of Philosophy at SUNY Fredonia. Here I'm going to be talking about demonstrating invalidity in predicate logic, and in particular using the finite universe method to show that certain invalid arguments are invalid in predicate logic. And sometimes this is called the model universe method. And I'm going to be using the power of Logic Web Tutor here. I'm going to click on 9.2. This video will supplement section 9.2 of the book. Okay. This method is actually a method that, in principle, can be used to tell whether an argument is valid or invalid, as the case might be, as long as we're dealing with only monadic predicate logic. But in principle, that is the case. But in practice, it can get a little bit unwieldy because, for example, if you have something like, 3 predicate letters, something like here, A, B, C, you would need to test a universe of 8 individuals, 2 to the power of 3, 2 to the power of 3 different predicate letters. And if you couldn't find validity in a finite universe containing 8 individuals, you could conclude that the argument is in fact valid. But again, that's kind of impractical, and it only holds in principle for monadic rather than relational logic anyway. So here I'm just going to talk about using the method with smaller universes on some of the problems here. I'm going to start with number 8. Okay. Number 8, the argument says there exists an M thing, that's the first premise, and there exists an N thing, the second premise. Therefore, there exists something which is both an M and an N thing. Okay? Don't get tripped up by the fact that the variable here is Z. If it were X, it would be exactly the same thing. Okay? There's no difference in meaning at all. The authors just happen to choose Z here instead of X. Okay? If M is monkey and N is noodle, this argument basically asserts that a monkey exists, at least one monkey exists, and at least one noodle exists, but therefore there is something that is both a monkey and a noodle. Okay, so that establishes on an intuitive level that this is an invalid argument. I'm going to click on that. So we're supposed to use the finite universe method to show that this is an invalid argument. And the first step in this method is to select a small, abstract, finite universe, sometimes called the model universe. We're going to need more than just a one-object universe here, because if you think about it, forget about the quantifiers. This argument would just say MZ, NZ, therefore MZ and NZ, and by conjunction that is a valid inference. So the next step is to go to a two-object universe. Okay, so here we're going to translate or expand the premise. Well, what does there exists an M thing amount to in a two-object universe? Well, it amounts to A is an M thing, or B is an M thing. Okay, so an existential statement, as this is here, becomes a disjunction of its instances, and this is a very simple statement. An instance of MZ is just something like MA or MB. Same thing with N here. There exists an N thing. Well, if there's only two things, A and B, that means that NA or NB. Okay. The conclusion is a somewhat more compound, categorical, quantified formula. It says that something is M and N. Well, that means that MA and NA, and here's where the disjunction comes in, or the existential, that corresponds to the fact that we're talking about an existential. So either A is this MN thing, or B is this MN thing. So MB and NB. Okay. I'm going to check that those are equivalent to the quantified formulas given this little finite universe. Seems to check out. Okay. And it sets me up with an abbreviated truth table. That's the second step in the finite universe method. The top row of the truth table is what I just keyed in for premises and conclusion. Okay. So basically here what I want is to suppose that this argument can have true premises leading to a false conclusion. Okay, that's the first step in the abbreviated truth table method. I'm looking at my conclusion. It's a disjunction. The only way that a disjunction can be false is if both of those disjuncts are false. So this right disjunct, that conjunction has to be false, as does this one. Okay? Okay. Basically, what I am kind of imagining here is a universe where I have an A thing, an A, little a, and little b, and I'm going to make A, for example, a monkey, but not a noodle. And I'm going to make B, I could do this the other way around if I wanted to, but B will be the noodle, but not the monkey. Okay. Envisioning a universe like this is more useful with simple arguments of this sort. It kind of helps do the truth table a little bit more quickly. So I'm going to make A a monkey and B not a monkey. Okay, so A is going to be my monkey, which is not a noodle, so that keeps my conjunction false there. And B is going to be my non-monkey, which keeps that conjunction false, but it's going to have to be a noodle. Okay. Why does B have to be that noodle? Well, that's going to make this disjunct true because the NA part of it is false. Okay. And B, being a noodle, is not a monkey, so that's going to be false. And that disjunct is going to be made true by the A thing, which is an M thing. Okay. So here I have made premises true and conclusion false, so I've confirmed the supposition that the argument can have true premises leading to a false conclusion, so I've shown that it's invalid, and I'm going to write down what I keyed in. MB is a false statement, NA is also false, and NB is true. Okay? I'm going to scroll down and check that. And that seems to work out. Correct. Okay. So there was an argument where we had a simple quantified formula as a premise, another one as another premise, and a quantified formula as a conclusion. I'm going to go backwards actually. I'm going to do this number 7 one, okay? I'll highlight it for you. There, okay. Notice that the premise here, there's only one premise here. The premise here is actually a conditional statement. It's a truth functional compound of two quantifier statements, and the conclusion is a quantified universal formula. Okay? So I'm going to say a little bit more about that as I go along here. Okay. Here is another case where I'm going to need at least two objects in my universe. And if I think about it, forget about the quantifiers, okay? I'm going to have like hx, then not jx, therefore jx, then not hx. That's actually going to be valid, okay, because one of them is the contrapositive or close enough of the other. So we're going to need at least two objects here. One object universe is not going to do, okay? Here's the way I want to think about this premise, okay? The main operator is that arrow, the arrow, okay? So that's got to stay in there. Now I'm just going to work on what's to the left of the arrow for all x, hx. In other words, everything's an h thing. Well, in an AB universe, that simply amounts to HA, and remember, for universal, it's a dot, HB. Universals become conjunctions of their instances. So if everything is H, in other words, if HA and HB, then I want to say everything is not J. Okay, well, that's going to be not J, not JA, and not JB. And that's the way to deal with a premise like that, where you have a truth functional operator, like an arrow in this case, that's already in there as the main operator of the statement. The conclusion here is a quantified formula, so it becomes a conjunction of its two instances. So JA arrow not HA. Okay, that's, again, I took the for all x away, and I put in the name A for the variable x. And since I'm dealing with a universal statement here, it's going to be a conjunction, and I'm going to do the same thing for B. If JB, then not HB. Okay, I'm going to check that. I was given two little green check marks there, which means I did okay. And it gives me the abbreviated truth table that I need to do. Okay. I don't know why we get all those squiggly lines there, but okay. Basically, this argument has one premise, which since I'm doing the abbreviated truth table method, I want that to be true, and I want this conjunction of a conclusion to be false. Okay. If I want this conclusion to be false, I want at least one of those if-thens to be false, and I don't think it really matters at all which one you go. So an if-then statement is going to be so for example, suppose I want this if-then to be false. Okay, then that's going to have to be true, arrow, arrow, false. So what's false there is not HB. So HB itself is going to be true. Okay, so I made the conclusion false by making kind of the right-hand conjunct false there. So to do that, I made JB true. So I'm going to kind of filter down these values. I made JB true, and I'm hitting delete to keep things lined up. That makes not JB false. All right. Which automatically makes this conjunction false, right? Okay. But I want my first premise to be true. It's an if-then statement. So therefore, this if part, the antecedent, is going to have to be false as well. Okay. And if you look back here, HB is true, so I have to put that value in. True. Okay. So if I want that conjunction to be false, my HA is going to have to be false. Okay. I'm working a little bit quickly here, but I'm not fooling around. So HA is going to be false, meaning not HA is going to be true. Okay. Since I've already made the conclusion false, it really doesn't matter. And since I've already made the premise true, it doesn't matter at all what JA is. Okay. Maybe I'll make it true. This is going to be true no matter what, because it's not HA is already true, the consequent of that conditional. And so I made JA true, just for completeness here. So not JA is going to be false. Okay. Okay. So I think I've confirmed the hypothesis that we could have a true premise leading to a false conclusion here, showing this argument to be invalid, and therefore really showing that predicate logic argument that we started with to be invalid. I'm going to read off what I wrote here. HA I made false. HB true, JA true, that's the one I think that didn't matter, JB true. Okay, and I'm going to check that. Okay, and this gives, somewhat decent feedback if you don't get the correct answer, but that one is correct. I'm going to do one more short one just to kind of make a little bit of a point here. I'm going to go to number 13. Okay. So this argument, again, the variable is a y, but it doesn't matter what that is. If it were an x instead of a y, it'd be exactly the same in meaning. So all A things are B things. BD. D is a B thing. Doug is a barbarian, whatever. Therefore AD. Okay. The idea here is we have here sort of an individual constant D, a name, in there in the argument. Okay, and the computer makes this easy on us actually, because it kind of tells us, it doesn't give us a choice to exclude D from our universe. And the idea here is BD is a premise of this argument. So the name D is in there in this argument. So D is going to have to be in your finite universe. Okay. So if you see an argument like this and you're not using a computer, you've got to, in this case it's D, you've got to keep that name in your universe as one of the things in your universe. Okay. I think we're going to be able to get away with a one-object universe here, just D. So for example, if I do that, then my premise is going to be if AD, in other words, if D is an A thing, then BD, D is a B thing. And my conclusion, I don't even have, my second premise, I don't have to rewrite at all. BD is not a quantified formula at all, and that just stays the same as BD. And I guess the conclusion was just AD here, so that stays the same. And the reason why this is going to work in a one-object universe is this is not valid. This is, you might remember, this is the fallacy of affirming the consequent. Okay, so that's all correct. My three translations or expansions, two of them which I didn't have to do any work at all. Okay, well, again, I want my first premise to be true. There's a second premise here which I want to be true, and I want my conclusion to be false. That's just the abbreviated truth table method. Well, AD I made false to make the conclusion false, and BD I made true, so that works out. Okay, that's a true premise, a true second premise, and a false conclusion, showing the argument invalid, and therefore showing that predicate logic argument to be invalid. Okay. So I hope this video was helpful. It's impossible to do every sort of invalid argument you might see with this method, but I hope it was helpful with respect to the parts of this method, translating or expanding formulas with quantifiers into those without quantifiers, and in a small finite abstract universe, and using truth table techniques, in this case the abbreviated truth table, to show that the argument given is invalid.